Okay, so we're going to work through this exam question. So if we read what it says the aldehyde, and then it gives us a condensed structural formula, reacts with potassium cyanide followed by dilute acid. So that's going to be a source of H plus ions. Right, so it's going to be a source of H plus ions, and it's going to form a racemic mixture of two stereoisomers of, and then it gives us the product, structure of the product. And so one thing to always bear in mind is this information at the beginning here. Yes, it refers to question 1, but it's given before any of the subparts to the question. So in A, B, C, etc., anything that's being asked about in those questions, we may need to look at this information right at the beginning, because this information could apply to any of those different question parts. All right, so the first question, or the first part, 1A, is asking us to give the UPAC name of the product of the reaction. And when we're thinking about naming organic compounds, one of the first things to do is to decide what's the suffix going to be, right? And we need to consider what functional group or groups there are. And in this compound here, there are two functional groups. There's that CN, which makes it a nitrile, and there's the OH, which makes it an alcohol. We can only have one of those in the suffix. We can only either describe something in this case as an alcohol in the suffix or as a nitrile, and a nitrile takes precedence. So it's going to be something nitrile. The next thing then we need to do is we need to count how many carbons there are. So we have the sort of stem part of the organic name, and the nitrile is the principal functional group in this compound. That is going to be where the first carbon is. So we've got 1, 2, 3, 4, 5, 6. We've got 6 carbons. So we have clearly got hex. Now the rest of the molecule is saturated. So it's going to be hexane. When we're naming nitriles, we do actually put the E in. We don't use the E normally, like in an alcohol or whatever. So hexane nitrile. And we've still got to we've still got to feature the OH group, the alcohol group, the hydroxyl group in the name of the compound. And we can see it's on the second carbon. So it's going to be 2-hydroxy hexane nitrile. Sorry, I don't know why I put nitriles there. Sorry about that. So hexane nitrile. And remember, you separate numbers and words with a dash, and then words themselves are, there are no gaps between words unless that's a particular feature of a name, like in an ester or in an acyl chloride. So our answer to that is 2-hydroxy hexane nitrile. Okay. All right, the question B. So describe how you would distinguish between two separate samples of the two stereoisomers for that particular compound, for that 2-hydroxy hexane nitrile. So we can appreciate these stereoisomers are optical isomers. So if you remember, stereoisomerism, there are two forms of stereoisomerism. So it could be geometric, or it could be optical. And geometric is a feature of alkenes. And optical is about non-superimposable mirror images. So in this instance, we are not talking about geometric, we're talking about optical. So we have to think about how we determine or distinguish between optical isomers, and what we use is we use plane polarized light. Now in the mark scheme, the key part here is polarized light, so they're not so picky on the plane bit, but I would get into the habit of referring to the plane. Plane polarized light would be rotated in opposite directions. By the two enantiomers. And enantiomers is a term that we use when describing optical isomers. So that enantiomers come in pairs. So one of those enantiomers would rotate the plane polarized light in a clockwise direction, and one would do it in an anti-clockwise direction. And this question is worth 2 marks. So we would be getting 1 mark for saying polarized light or plane polarized light, and then we'd be getting the 2nd mark for making it clear that that polarized light is rotated in opposite directions by the 2 enantiomers. And a key word. So a word you absolutely must use in your answer is rotate. So that's how they want it referred here, okay? So it is the rotation of the plane polarized light. All right, so moving on to the next question, or the next part. So it's asking us to explain why the reaction produces a racemic mixture. And it's very important to pay attention to the fact it is asking why. Sorry. It's asking why. So you're having to explain basically why are you getting these non-superimposable mirror images? Why are you getting optical isomers? What is it about this reaction that is causing that? So it is about what is happening in the reaction. So the reason, it's a 3-mark question. The first thing is that we have to think about the shape of the molecule around the planar, I've just given the shape, around the carbonyl group. It is a planar carbonyl group. So, so the planar carbonyl group, so that is the bit that's being attacked in this reaction. So this is the feature of the aldehyde that's being attacked. The planar is absolutely fundamental, so you must have that term, planar. And then you've got to be very careful about how you describe what actually is planar. So they won't accept a planar molecule because the rest of the molecule might not have a planar shape. So actually in this particular molecule, the rest of the molecule is tetrahedral around each other carbon, because each of those has 4 single bonds. It's not enough to say planar bond, because I guess technically all bonds are planar, and you can't say planar carbonyl. So you must make it clear it's the group. So another way that you could have described or shown the planar group is to draw it. So we're saying that is planar. We're not saying the C double bond O is planar. We're saying that where we've got those 3 different groups attached to that carbon, that's a planar part of this molecule. So that carbonyl group is planar. And what that means is that the nucleophile, or that planar carbonyl group can be attacked from either side, or from above or below, but I'm going to put an attack from either side. Okay, so that's our 2nd mark with equal probability. Or chance, or whatever. So it's a 3-mark question. We're making it. We're explaining the whole thing, but we're making it clear that it all stems from the fact that the carbonyl group is planar. That means it can be attacked from either side. So if we were wanting to just sort of illustrate that to ourselves, it can be attacked from above, or it can be attacked from below. And it can be attacked with equal probability, so it's just as likely to be above as it is to be below. So as a result, we would get equal amounts. So this word equal is fundamental. So as our 3rd answer, so let's give a 3rd answer. So I'm going to put a slash here to say that this is an alternative to the with equal probability. Attack from either, so it can be attacked from either side, producing equal, so there's that word, very important for this particular answer, equal amounts of the two isomers or enantiomers of the two isomers. Okay. So here, this is a very interesting question. It's only worth 2 marks, but actually this requires some careful thought. So they're telling us that an isomer of our original compound reacts with potassium cyanide followed by dilute acid to form a compound that does not show stereoisomerism. So they're not talking about a racemic mixture, because a racemic mixture has 2 optical isomers. This is saying that there are no optical isomers produced. Okay, so let's just make a note of that. So no optical isomers produced. So then it asks us to draw the structure of the compound formed and justify why it does not show stereoisomerism. So this is quite tricky in a sense. This is something you're either going to see quite easily or not. So I'm going to try and sort of explain why the answer is the answer. So if it's an isomer of the aldehyde, they haven't told us it's a functional group isomer, so we just have to simply, well, maybe it is a functional group, but I think what we've got to assume here that we're talking about a ketone. It doesn't explicitly say it, but the fact that it's saying the isomer does react with potassium cyanide and dilute acid, it must have that carbonyl group. So we've got to assume it's got a carbonyl group, and if it's not the aldehyde, it must be a ketone. And if we think about our carbonyl group, this is our carbonyl group, and we have 2 other things attached to the carbon. But when this reaction takes place, this is how the carbonyl group is changing. And for something to have optical isomerism, what it's got to have is a chiral carbon. And that means a carbon that has 4 different groups attached to it. And if it's going to have optical isomerism in a reaction involving an aldehyde or a ketone, then we're looking at, then the chiral carbon has to be, or there has to be a chiral carbon where the reaction took place. What the carbon that was the carbon in the carbonyl bond, or carbonyl group, sorry. So for this to be a chiral carbon, that's got to be one type of group, that's got to be another, that's got to be a third, and then finally we've got to have a 4th. And if we're thinking about this reaction with our isomer, we can't do anything about the OH. We're going to make the OH group. We can't do anything about the CN because we're going to make the CN group. So what we're really saying is that we need to have a product in which we do not have different groups either side of the carbon that we've got bonded to the OH and bonded to the CN. So they must be the same. So we've got our aldehyde is 5 carbons. So the way that that's achieved is if we have the carbonyl essentially with a line of symmetry, so that the groups attached to the carbonyl are the same on both sides. So what we're looking at then as our answer is, so the ketone that we've got to have that's going to do that is going to be, it's going to have the carbonyl with the same on both sides, and it's a 5 carbon molecule, so that's a 2. So that's what the ketone has to be. And we can see that we're changing that carbonyl group to have an OH group and a cyanide group. So that means that the molecule, the structure of the compound formed, is going to be this. Okay. And in terms of our justification, well, you know, I've tried to give an explanation as to how we might have arrived at that as our sort of deduction. And let's just confirm to ourselves that we've got one group there, we've got another group there, but both of these are the same. So making that connection with what I've drawn in the top right, or toward, you know, sort of northeast there. So our justification, we don't have to say very much. So we can simply say that it does not have a chiral centre. That's justification enough. But other things that we could say is it does not have a carbon attached to 4 groups. That's how we were working it out. Or attached to 4 different groups, I should say, not 4 groups. So that's how we deduced that to be the answer. Or we could say it's attached to 2 identical groups, which are those ethyl groups. Or we could say it was symmetrical. Those would be all acceptable, but I think these first 2 are probably the best in terms of you thinking about future questions. So I hope that was useful and helpful, and I would appreciate your feedback on that as an example of working through an exam question, and so that I can think about how to do future ones. Thanks.